Good afternoon everyone. Thank you for joining Mr. Ish on this video. We will be talking about a new subject over here. It's still derivatives, but we're talking about a new aspect of derivatives, an easy subject. It's going to be higher order derivatives. Up till now, all the questions we've looked at were the single order derivatives, or we took a function and we just did a derivative on that once. And when we did a derivative on that function, we obtained a rate of change. When we're talking about higher order derivatives, you're talking about multiple derivatives in this following sense. If you take a derivative of a function, you've done it once, and then on that answer, the derived answer, the rate of change you've obtained, you take that answer and you do the derivative on it again and then again. These are called higher order derivatives. In terms of practicality, you want to go maybe as far as second order derivatives. You can go up to third order derivatives, but the more derivatives orders you keep adding, you lose the practicality. So if we started with a function up till now, we've done a derivative on this original function and we've obtained this answer over here. This right here is first order because we've done a derivative once. So what we've done over here is we've obtained a rate of change, ROC, rate of change. If we take this answer over here, which we've obtained from the original function, and now we do another derivative on this, and we end up with another derivative, a derivative on top of our derivative. Now we're talking about second order derivatives. And now what are we getting? We're getting a rate of change on a rate of change. So we've done a rate of change on a rate of change. That's second order derivatives. And when we get to second order derivatives, we're talking about higher order derivatives. Now if you talk about the second order derivative, this answer you received, and you do a derivative on top of that, you know what we're doing here. We're doing a third order derivative, and you're doing a rate of change on a rate of change on a rate of change, and you can see how this goes. But in terms of practicality, from what I have seen, these are the most practical. Once you start going into third order derivatives and higher, you end up losing practicality, because what are you doing then? You're just doing an exercise of just learning how to do derivatives on top of derivatives. But the whole process of higher order derivatives is easy, because if you know how to do derivatives, you know how to do higher order derivatives. Because who's to say that your original derivative was not just a normal function, and now you're viewing that as just a first order derivative of a function, of an original function. So you can always look at it that way. If supposedly you're tasked with finding higher order derivatives, just assume what you're starting out with and what you're receiving each time, each of those loops, that you're starting with a fresh new function and you're in your head just doing a first order derivative all along. So by means of techniques, there's no difference between a third order, second order, first order. The difference arises in terms of the practical significance of these higher order derivatives. So when it comes to higher order derivatives, the most benefit is usually the first order and the second order in terms of practicality. After the second order, you end up losing the practical significance. And a very good example of a function which is beneficial in terms of its second order significance is acceleration. If you think about what acceleration is, acceleration happens to be a second order derivative. If you think about a moving object with respect to time, an object is moving over a period of time in a straight line, and imagine its function equation was equal to just an s. If you were to take the derivative of just this moving object with respect to time, the first order derivative, you know what that first order derivative would represent. It would represent its velocity. And you could represent that with respect to time in the following way. You would have velocity with respect to time. It would be represented by the derivative of that object, moving object with respect to time, and you could say it would be ds over dt. And this ds or dt is no different than what I've been showing you all along, dx over dy, the derivative with respect to this moving object over a period of time. This velocity over here would be a first order derivative. It would represent a first order rate of change. Remember, we're not getting into anything too conceptual here. We're just talking about why do we have to even bother learning higher order derivatives, and higher order derivatives are easy. And if you were to take the derivative of this velocity value which you have obtained, the first order derivative, the velocity, if you were to take a derivative on top of this, now you know what you're getting into. You're getting into acceleration. The acceleration would be a second order derivative over here, having a practical value, because it would represent the instantaneous rate of change of that velocity over a period of time. this would be a second order derivative. And how could you represent that? You could represent that the acceleration with respect to time would be the velocity with respect to time, the velocity derivative with respect to time, or it could be the second order derivative of the position with respect to time. And you could see clearly over here that acceleration was a second order derivative. You could also say, you could also look at it in this way, d square s or dt square. So this right over here represents what a second order derivative looks like. Anytime you see this type of notation next to your question, the question is no longer talking about first order derivatives, it's talking about a second order derivative. And acceleration is an example of a second order derivative, velocity is a first order derivative. You have to contrast this with what you've been seeing all along, d over dx, or d over d theta, or d over dt with regards to what your variable was, x theta, or t. These are all variables. Derivative with respect to x, derivative with respect to theta, derivative with t. But when you see over here, now you're looking at something which is second order by virtue of these squares which are showing up. You can visualize it as such. D square y over dx square, you can visualize it as this. All of this giving you that. And this is what I'm talking about over here. This is the notation over here for a second order derivative, and this x can be replaced by whatever variable we have in our function. It could be x, t, theta, any letter. Alright, but look for these powers over here. They'll clue you into what the question is looking for. So let's look at some examples. And these examples are not hard because higher order derivatives are just taking a derivative on top of a derivative, and you can always assume you're just doing a single order derivative even though you're not, because the whole process of taking a derivative is no different whether it's first order, second order, or any order. And we're going to look at some of these questions from this calculus book over here, d square over dx square, and our function is this for which we have to find the second order derivative. How do we know we have to find a second order derivative? By notation over here. It tells us we're finding the second order derivative. And you know this is an exponential function, so it's not a foreign function by any means. It's easy, it's what you've seen. You know you want to first find the first order derivative, and then what the result is, you find a derivative of that. So let's proceed, and you know you have to use a chain rule because we have a composite function. If u is equal to minus 3x squared, and this right here is why I was saying we're not going to be looking at too many examples, because they're just like looking over general derivative questions. Now you do the first order derivative, d with respect to u is e to the u, and then du with respect to x, you can write minus 3x squared, and then you do the regular derivative over here. E to the u is e to the u, minus 3x squared derivative is a minus 6x. You bring everything together, minus 6x e to the minus 3x squared, where you resubstitute it, and here's your first order derivative over here. Minus 6x times e to the minus 3x squared. Now you're still tasked with finding a derivative of this because we're doing a second order derivative. See, second order derivative. Now you have to do the derivative of this, and you can rewrite it in a friendly way by bringing this coefficient out. You have x e to the minus 3x squared. Now look over here, you have a product rule kicking in because you have a function over here, f function, a g function, and you have a composite function on top of that. Remember, no different than what you've seen. You could have pretended this right here was your question. Now you're just finding a first order derivative like I was alluding to from the very beginning. You can always view each of these questions as a first order derivative. Just view that each step is a new step of a new question. Anyhow, product rule template, you do minus 6 times all of this in terms of the product rule. E to the minus 3x squared times the derivative of x plus the f function times the derivative over here of the g function, which is composite. You're going to d over du. You can do many of these substitutions in your head now. E to the u and then du over dx. You can have minus 3x squared. Now look over here. We have to come over here and we have to open this up. Minus 6 times e to the minus 3x squared, because the derivative of x is just a 1. Now look over here, minus 3x squared derivative is a minus 6x. Minus 6x multiplies with this positive x gives you minus 6x squared. And then you still have e to the u, you can resubstitute minus 3x squared and you end up with this. Now look over here, if you open up everything, you get minus 6e to the minus 3x squared plus 36x squared e to the minus 3x squared. You can substitute, you can isolate. You have 6's here and you have e to the minus 3x squared. You can isolate a minus 6 and you can isolate a e to the minus 3x squared, and within the parentheses you will get a 1 over here because all of this goes in this one time, and here you get a minus 6x square. You get a minus 6x square. If you isolate, you'll get that. Now you can still rewrite this in a better way, and the better way is this. You can do minus, you can hit everything with a minus. You can do positive 6 times 6x square minus 1 over e to the 3x square. I'm just bringing this negative exponent down, and this can be a good final answer right over here. 6 times 6x square minus 1 over e to the 3x square. Or you didn't have to hit everything by minus 1. You could have done minus 6 times 1 minus 6x square over e to the 3x square, and your answer would be still fine that way. So as you see in this question, there was nothing different in it in terms of technique. Here was your first order answer right over here, your first order derivative, and this right here is your second order derivative right over here. And that is represented right here in this notation. Let's look at a few more examples, and that'll be it for this video. So when you're looking here at this question, we're tasked with finding a second order derivative of this function, which is a product of two functions, f and a g function. Here's my f and here's a g, and you have to be thinking about the product rule. So we have to proceed as such. We have to first find the first order derivative, then with the result we'll find the second order derivative, and it wouldn't be hard. Look over here, let's follow the product rule. You'll have the g function multiplied by the derivative of the f function plus the f function multiplied by the derivative of the g function, which is composite. You have to do a substitution. If u is equal to 2t, then f of u must be equal to ln u. Derivative with regards to u, ln u, and then derivative with regards to the t is a 2t. When you solve all of this out, the derivative of t is just a 1. You get a natural log 2t, and look over here, plus derivative of 2t is a 2. 2 times this t is a 2t. And the derivative of natural log u will be 1 over u. But u represented a t, 2t, so it will be 1 over 2t divided by 2t. And what do I get? This cancels out to a 1. It will cancel out to a 1. So my first order derivative is natural log 2t plus 1. Natural log 2t plus 1. Now we have to find the second order derivative. This is my first order. Now we'll find the second order derivative. And my second order derivative will arise from the rate of change of the first order derivative. We're going to find the derivative of that expression, or the natural log 2t plus 1. The 1 over here is meaningless because it'll zero out because it's a constant. You're only basically looking at the derivative of this, and you're going to just use the chain rule. Derivative with regards to u, we have a natural log u, a substitution over here, and du with regards to 2t, with regards to dt, and you have a 2t. All you have to do is take this to completion and you're done. Natural log u derivative is 1 over u. Multiplying here, 2t derivative is a 2. What do you get? 2 over a u. And what does that yield you? 2 over a 2t, and you get 1 over t, and you're done. So this represents your second order derivative, 1 over t, and you're good. Remember, these higher order derivatives are not hard. If someone had tasked you had to find a third order derivative, you just find the derivative of that, and it wouldn't be any harder than what you already know. It'd be easy. Let's look at 2 more questions and we'll wrap it. So our function is this, sine x squared, and we have to find a derivative, the second order derivative of this. And you would have to start by finding the first order derivative and recognizing that you have a composite function. You would do u is equal to x squared. Therefore, function with regards to that u is equal to sine u. Sine u. And then you proceed with that derivative. And here we're doing the first order derivative step right here. Derivative with regards to u is a sine u, and then the derivative with regards to that x is a x squared, and you're just finding this sine u derivative as a cosine u, and the u over here represents an x squared, and the derivative of x squared is a 2x, and this right here is your first order derivative done. You could have written 2x first, 2x cosine x squared. You can say that 2x cosine x squared, and this right here is your first order derivative. Now you have to find the second order derivative and view it as just like a whole brand new question, that this is your question. You have to find the derivative of that. It's a product of two functions, one of which is a composite function, and you have a coefficient. You can view it entirely as this d over dx, x cosine x squared, and this right here is my question. I have a f and a g function, and I have to use a product rule, and that's what I'm going to do. 2 multiplied by the product rule template here. The g function cosine x squared multiplied by the derivative of the f function plus the f function multiplied by the derivative of the g function, which is a composite, so we have to do a substitution. Again, u is equal to x squared, f of u is equal to cosine u. So we'll have a cosine u, and derivative of u with respect to x will be an x squared, and we'll just take this to completion and our second order derivative will be done. Look over here, the derivative of all of this right here is just cosine x squared, because the derivative of x is a 1. Now look over here, x squared derivative is a 2x. 2x times that x is a 2x squared. Derivative of cosine u is a minus sine u, but u represents here an x squared. All we gotta do is marry things together. We have a 2 cosine x squared when we open up the parentheses. 2 times this 2 and a minus is a minus 4x squared sine x squared, and we're done. This here represents our second order derivative, a rate of change of a rate of change. So as promised, this is our last question. We have to find the second order derivative of this function, tan minus 1 inverse tangent of s. And you can see our variable here is an s. The variable can be any letter, it doesn't matter. And you have to proceed like this, as you would already know, as if you're doing the first order derivative, which you will. The first order derivative, and you know you have to find the derivative of this. And you should remember the template for a tangent inverse is always 1 over 1 plus x squared. The derivative follows this scheme over here, 1 over 1 plus x squared. So the first order derivative is easy because this is not a composite function by any means. It's easy. Your answer right here, first order derivative is 1 over 1 plus s squared, and you're done. This right here is your first order derivative, which is representing the rate of change of your initial function. Now when you do the second order derivative, you're basically taking this function over here and you're doing the derivative on that, the second step, 1 over 1 plus s squared. Now you can see we have no trigonometric function at play over here. We basically just have the quotient rule at work, the quotient rule. This is my g function, that's my f function, so you follow the scheme of the quotient rule. The g function multiplied by the derivative of the f function, which will zero everything out over here, minus the f function multiplied by the derivative of the g function all over the g function squared. Now look what happens, the g function squared. This derivative of a constant is a 0, this zeroes out. We have a minus and everything over here. What's the derivative of this numerator going to be? A minus 1 times derivative of 1 plus s squared is a 2s over 1 plus s squared. You don't even have to open up the denominator. Your final answer will be a minus 2s over 1 plus s squared, and you will be done. So with this example, we pretty much wrap our video up. You can see it was not a difficult topic. It by means was not at all a difficult topic, because higher order derivatives are significant in terms of their applications, but in terms of the actual procedures or the techniques, it's no different than doing a first order derivative, except you're just doing a derivative on top of a derivative, depending on how many times, but no matter what order it is, right? Eventually your derivative procedures will end, most likely because a variable will get consumed. But you cannot just keep doing a derivative upon derivative, because then you start losing your practical value. You only have to go up to second or maybe third order derivatives, and pretty much after that it's just a technique practice, and that's all what it is. But this higher order derivatives is a quick, easy topic, something which you may have already known, but I hope you enjoyed this video. Please stay tuned for more. Have a nice day. Bye.